course, I've also threatened to take my motorcycle down the hallway of the school my last day. So I may have a reputation sometimes.
You say this in the in the meetings and all.
Oh, I've told my president and dean that. I have to talk to the president a lot. I have to talk to the dean a lot. I have to talk to the chancellor a lot. And I tell them, you know, it's like anything we talk about is between us. I don't go running to the next person to say that, you know, you said this or that. But I will sometimes say things that just for the shock value. Right now I'm pushing for lab upgrades.
Actual equipment, you mean?
Equipment and
The labs itself.
the actual furniture and supporting. So there's times when they see me coming down the hall, they'll duck down a stairwell or something. Because they know what the topic's going to be. No, this is at my school. I don't stir trouble up here. I'm just a grad student. I do not have authority here.
So Luke, if I'm not wearing a mask, is that,
Yeah.
you know? Two out of 5 is wearing a mask. Maybe it's not bad to wear it.
When I'm in solid state, because we're in 404, it's actually, we're so far apart from each other that it's really,
Yeah.
we meet the distancing requirements.
Why is that? You're missing Arya and Michael.
Crying into their home.
It's that bad, huh?
Is this the last session for the exam or?
Everyone is wearing masks. I have to.
Is this the last
Oh.
session for the exam?
Yes.
So this will be.
I think yes, in the sense, okay, here is what I thought. Raw wrote me an email yesterday saying that this homework 7, I think, the one on conservation principles, was really hard on him. He was struggling, so I gave it a thought, and I feel that, and yeah, Abdullah also came to my office hours when he was asking questions, which I felt were very relevant. And I was not having easy answers to this, or I was not able to clarify them. So I was thinking that today, whatever I was thinking of doing Poisson bracket, but it is the same, I will be doing the same. But probably this will help that. That's my feeling. Not directly in the sense of the homework, whatever we are doing, but more in the sense of a concept. What are we asking? Like, what is this we are doing? So in that sense, I feel, yes, let's have today's work for the exam. So I think it will get connected in that sense. And we will finish it after today, and we will start Kepler problem after the exam. So that will give us 4 weeks, and Kepler problem and special relativity. So I think that might be the good way to close. So that's my answer to that. Answer it? Yeah. Right, sounds good.
It's the one downfall of dry erase boards. I like writing on them better, but you have to make sure you have plenty of markers.
Yeah. So you prefer this over chalkboard because you must have come from the chalkboard generation.
Oh, yes, I wanted to keep my chalkboard,
Oh, yeah, you did one. But
And
you
then-
said you like
but then I started using dry erase
and you like this better.
and I started liking it better.
Oh, So this will cover everything until today, the end of, or including the homework that's due on. And so you guys say that you guys are all struggling. Is that true for everyone? With the you have a comment?
I'm still working on it.
Like I was wondering if take home will help making it take home, but then some of you guys might have other take homes and this might. I mean, is take home okay? How about it? Is take home going to help you guys or is it sometimes worse?
You mean the midterm?
Yes, the midterm will be take home, like we can take home. To a certain extent, even discuss.
Will it be more difficult?
It will be like the homework, yeah, but it might be a little longer. Yeah, like midterm one, for example, I asked very small questions. It has to be finishable in 1 hour. It's a challenge. But this could serve for those who really try to do it carefully, and if you make it longer, then it takes double the amount of time. So sometimes it could hurt also. Yes.
So can we discuss it as well or no? We have to skip
Yes, we can discuss
with you or with each other?
with each other, perfect. With or with me also. Yeah, you can do as like in homework, but don't ask too much. Don't ask me to give every step, kind of, right?
Would we do Tuesday?
Yeah, so that since I'm doing this at this final notice, I can even do more time. Like I can be flexible about that in case you guys have other things due. But you don't want to delay this too much.
Right.
Like if these things overlap or pile up, and it gets hard to handle unless you're too very organized. So how about this? There will be a good percentage of it that is take home with a significant amount of flexibility in when to submit, but not surely in the end of April. That's too late. Like let's say within the next week or 10 days or something like that. Like that's something like that. And I'll still put one question in the midterm so that I'm told that many times during the exam, you try to compile all the topics together, and even that helps. Like just the fact that you collect all your thoughts together, just working towards the exam helps. So for that purpose, you will have to come here, and there will be one question. So very small percentage, let's say 25% of it, we will have it in plus, so that you work for it, and then mostly the grades will be decided. Does that seem fair enough? So So which puts in more pressure than make a homework or the proper exam. So we introduced the idea of Poisson bracket. And this comes from our earlier evaluation. We did the variation of the action under general arbitrary transformations, and we got the equations of motions. And once the equations of motions is used, then we say that the action will change according to certain form. So for now, the content of those things is that is equations of motions. Let's call it Hamilton equations of motions. And that is, if you were to think in terms of a general transformation in time, then you say that the rate of change of Hamiltonian with respect to time is equal to the partial rate of change of, like this is total change. That means to say it's the implicit variable also, and mostly the implicit variables are in position and momentum. And the second is variation with position. I think it's variation with momentum that leads you to this equation. This gives you the R by dt is equal to partial derivative of Hamiltonian with respect to t. And it's important to realize that the Hamiltonian itself depends on position, momentum, and time. That's your equations of motion, but typically it's not the only quantity you're interested in, right? This is position, momentum, and the Hamiltonian. Typically you're interested in something else. It could be you might be measuring the angular momentum, or you might be measuring the kinetic energy, or you might be measuring the various other quantities you build out of all these things. But everything typically depends on position and momentum and time. Those are the three fundamental quantities. And we would like to know how certain things change with time, but not necessarily under time. We also talked about how things change under rotations or under translations, and we would like to investigate them. And that is all we want to keep in mind. We have some equations of motions. These are constraints on the coordinates. Like it's not any coordinate we are talking about. A particle is constrained by these equations. It cannot freely move around. This is a constraint. So that's what we want to keep in mind. And next is, let's say, we think about any arbitrary function. Let's say this is f of r, t, and t. And in this case, the definition is clear. How does f change with time? We know the definition of partial derivative. So this is, and this could be any object. And we learned that this is partial derivative plus by dr dotted with dr by dt plus is that very clear? Like that's how you would change any function. Notice this has to do with the fact that there is an implicit dependence of position. And that should be straightforward. But now you can use equations of motions.
F is vector or scalar?
This, let's say it is a scalar, but even if it's a vector, it goes through. It's just that then we have to take care of the index. For now, it is a scalar. For now, F is a scalar. We'll talk about it being a vector almost immediately. Okay, if that's true, I can use these equations of motion anytime I want to, because now we're talking about actual physical quantities. Physical quantities evolve in under these constraints, if you want, or that's called the equations of motion. And we immediately have this is T plus and notice, I think just to add on to or emphasize on what Aryan was asking, these are vectors, right? This is F is a scalar. Once I take the gradient with respect to position, that's a vector. Gradient with respect to the momentum, that's also a vector. Those two have to be dotted. So this dot product is between two gradients, right? So I'll keep that in mind. And this will be written as, so this lets us define what is called the Poisson bracket. So notice there are two operators, F and H. Once it is being operated upon by derivative with R and P, and then you swap it, and then you subtract quantities, right? So there is a pattern in there. And anytime you see such a pattern, you define what is called the Poisson bracket. And this is very tedious to write it, but one has to write it because economic, if you don't write it, then it's confusing that this could be the quantum mechanical commutator. But it has the same properties which you do the homework and how distribute if there are two operators, what's the distribution formula. All that is interesting features, but those are relegated into your homework. And it's also, we can generalize this by saying that this could be with respect to any other operator, like y position and momentum, anything else. So to keep that general, often you also write this is R comma P. But in our situation, almost all through the course, that means to say that we will be doing this only for one more day or so. This will always be R comma P. I don't plan to do this for other variables. So since I won't be introducing quantum commutator, which is a quantum commutator, which is there in your homework, I can as well drop this, but I'll keep it just not to be lazy, just to emphasize that is. But that's what it is. And what is this? Without writing it, rewriting this, that boxed quantity is your is the Poisson bracket, and that's what is called the Poisson bracket. That's the definition of the Poisson bracket. At this stage, it seems very harmless. This is just a definition, right? There is nothing else, but there is a lot of meaning in it. The way one has to read this is, and we will the whole lecture I will be just repeating that with various examples. But what we want to do is that whenever we have a transformation, infinitesimal transformation, let's say, transformation, always can be written as some operator, let me call M, dotted with, there is some variable, if it is rotation, for example, it is delta omega. If it is translation, delta epsilon, there is, this is the what is it? Variables, parameters, right? Parameters. And these are generators. Example is for translation, this comes out to be momentum dotted with delta epsilon. For rotation, it is angular momentum dotted with delta omega. Is that clear what I mean? We did this earlier. For translation, this is P dot omega. For rotation, L dot omega. For translation in time, it is H times delta S, let's say. So those are all possibilities, but always what we are looking for is that if you have any function f comma, let's say m, this is the variation of f under the transformation generated by m. So take this home and think about it. Everything else we do in the lecture, think in terms of this, that, and even the earlier homework, that's the message you want to take home. As to you change, so you're asking the question, if I change my coordinates, how does something else change? And it could be anything. It could, usually we talk about position, momentum, Hamiltonian. It could be angular momentum, kinetic energy. Like that's what I can ask in your exam. I have done position momentum a lot. Let's say kinetic energy, how does it? But kinetic energy is built out of velocity. Velocity is built out of position. So if you know position, it's just a matter of chain rules. Keep doing that. So that's a fundamental question we are asking. So let's do an example. The easiest is translation. Any questions before that? Okay, so let's talk about rigid translation. And by definition, rigid translation would be delta R. How does it change? I say it is a constant. There is no time dependence, no position dependence in this. We could talk about a translation where at each point there is a different push. Like I move by 10 centimeters, someone else moves by 3 centimeters, the third person moves by 5 centimeters. That is what's one kind of translation. The other is everything moves together. So when I say rigid translation, it means that it's uniform in every. Delta P we say is 0. No motivation needed. It's just that we should be consistent with these definitions. That's all. And delta T, let's say, is 0. So that's a translation. I mean, we call it translation. That's what we mean by that. And this is given to you. You begin from here. And now let's say, how does things change? I can say, I can put anything for F. Let's begin with R itself. I would like to know how would R change under translation? But I already know that R changes this way. Like that's what is given to me. This is change in R under translation, change in P under translation, change in T under translation. But I have a new formula for this. I'm also told that this is also true. So this is T dotted with epsilon. Okay. And one would say, oh, is that really true? That if this is correct, if it is consistent, we should get this out of this. So let's see how it works. So we say
This Poisson bracket.
that again. Yeah, this is, oh yeah, I meant to write that. I said I will keep writing and I forgot. Promised I will write. I'll always use Poisson bracket in this lecture all through. Okay, what is this equal to? And we immediately see that this is a vector coming in, right? Now we have it like this, I defined it for a scalar, so this is a vector. So let's switch this. That vector sign stands for this. This is a dot product. Let me add an index there. That's I. That just clarifies that this vector stands for this vector sign, right? That would be confusion where it is. But in this case, there is no confusion because that's a vector that's a scalar, so it should be okay. So we can say instead of R, let me say this is R1. That's the first. It should be fine if we use dyadic notation, it goes through, but just to clarify, let's say this is this. So this is position R I. Forget that over delta R and d by dp of what was that doing? Yeah, p dot with. So why is it I not one? Yeah, I meant to write 1 here, but since you asked, I'll change that. I meant to do 1. I started by doing 1, but then I thought, oh, why 1? I do all of them. Okay. And now there are too many vectors, right? It should be confusing because now this is a free vector here, and now there is a dot product here. And this dot product is between whom? It is between these two vectors here. So let's call it J. And if you want, you can put a K also here if it is confusing at all. But I think it is clear that that's a dot product. That should not be confusing. And that is minus of the RI of the P J dotted index now D or I P dotted.
Do we need that dot product on the first term?
It's not. If you depend on your index, then it's not needed. Like I'm trying to do both at the same time. Like I'm used to doing index, dyadic notation, but I'm realizing that in the beginning, yeah, it's very confusing to me. I think it is the undergraduate students. Until you have learned it, you hate index notation. And once you have realized what it is, then you love index notation, then you don't want to use vectors at all. And for me, I like the vectors in the sense it gives me physics is more, insight is there. And index is, of course, more powerful. So you do less mistakes. So I like to do both in a sense. Okay. So this J, so I think you guys are good with index. So I'll do that. What is delta Ri by delta Rj? That's Kronecker delta. So this is equal to Kronecker delta Ij. And delta Pj, let's also put this K here. K. So that's delta Jk. You want, and that is a delta epsilon K. And this one is 0 right away because R with respect to P is 0. R does not depend on P, so that's 0. And this is nothing but delta epsilon I, which is delta bring back the vector towards this. Which should not be surprising, of course, we began with that, why not? I mean, but it's a consistency check. Right. Any questions at this stage? Notice what I have done. I've asked the question, how does R change under translation? Even though I gave it to begin with, I did it this time using the definition of Poisson bracket. I can do this for any quantity now. I can do this P now, but let's do more slightly non-trivial. Let's say, how does Hamiltonian change, or how does angular momentum change under translation? Right, that might be slightly non-trivial. Or how does angular momentum? There is an R there, there is a T there. If you think about it, you can immediately come to the conclusion. But let's do that. Okay, let's do how does let's do a scalar first, Hamiltonian, and then we'll come to the angular momentum. And whatever I'm saying goes through directly into quantum mechanics. You just have to drop this. And in that sense, this is the calculus. Calculus is how does something change when you make some other change, right? If X changes, how does Y change? That's what calculus is about. You make a small change, how does F change? So this is the calculus of, let's say, physical quantities. When you're having, or you can say calculus of dynamics. Right? Under the constraint that equations of motions are satisfied, how does a quantity change with respect to a small, infinitely tiny transformation? So in that sense, we are talking about dynamical evolution in that sense. Okay, so with that theme, let's proceed. And that first we will look at a scalar. Let's say, how does delta H, and to emphasize that we are talking about the transformation with respect to translation, I emphasize that this is not an arbitrary change in the Hamiltonian. This is the change in the Hamiltonian because of a translation, which is characterized by this. You can also put a vector sign if you want. So that's equal to H, comma, T dotted F. So that's
Do you have another marker?
oh, it's too light, huh? Is this better? Okay. So this is equal to how does the Hamiltonian change? So we say this is H by R dotted with is the gradient of the Hamiltonian, and then this is change in P of P dotted with. So is this readable? No? It's worse.
There's some more over on the.
Oh, better? Better?
Yeah.
Minus how does P dotted with epsilon change with P itself? There is a P here, and this is a constant. So when I'm talking about this, I just have to hit this on this. Derivative of P with P is the constant in front. That's it. Right. So this is equal. So H R dotted with delta epsilon, and P with respect to R, that's 0, right? So this gives you 0. This is anyway a constant, doesn't work. This gives you a 0, that's 0. So what we have learned is how does the Hamiltonian change under translation? That's this. And I have got it using Poisson, right? In your homework, what you ask the same question, but there you're more blunt. You say that I'm interested in the Hamiltonian. So H is R comma P and T. Right? And I'm told that R changes, P doesn't change. So what is delta H? Under translation, this is H of R plus delta epsilon comma P comma T minus of H R T T. This is in the limit that this is tiny. Taylor expand this, you get delta epsilon dotted with same thing. So everything is consistent. Right? It's the same statement. See, this is calculus, right? You would have said, oh, that's trivial. This is, I studied this in the first semester of calculus. But here we are seeing that the Poisson bracket has that information for any general transformation. So it is a much more deeper or general statement than this, or it is a calculus of dynamics in this sense. Let's next do what about angular momentum, right? How does angular momentum change under translation? So let's say this is L, comma P. So and when I write L here, it's understood that L is R cross P. It's built out of R and P. So this is equal to change in L, and this time I have to be working with index. So this is I, that's I, and when I say this is changing with R, that's a vector, so this is J. And that J is dotted with P by P J. This is P of K. These two. And minus of P by dt J of Li R K. And delta epsilon is not dependent on P. So clear what I'm doing? Like, is the theme clear? Any questions again, please ask.
That's the
Yes.
derivative for the index is I or J. Okay.
This one? This is J because this dots with this, right? Like this is the dot product here. This is this dot product. Right? So whenever there's a dot product, it means it's a sum, right? And that sum is encoded as J. Is that okay? Confidence? Did I answer?
No, it's just I.
Oh, no, I meant to say this is J. My handwriting. Better? Oh, or maybe it is in some, I don't know, it might be a, but this is J for me. Okay. Is that I in certain style of writing?
No, it's
Okay, it's just, okay, so this is J, right? Yeah. What is DLI by DRJ? So let's do that right away. Yeah, so let's do that independently then. What is D L I by D R J? This is E by D R J times epsilon I M N and R M E N. Is this notation clear for all of us here? Right? Index notation?
No, I have something.
Oh, it's okay. So here, what I'm using is that A cross B. This is C, right? Let's say this is C. That's a vector equation. This has three components. That's I. Right? I could be 1, 2, 3. And that will be given by epsilon I J K A J and EK. And here, since J is repeated, it means there is a sum on it. K is repeated, there is a sum on it. What this means is that this is I is equal to 1 to 3, J is equal to 1 to 3, and epsilon I J K A J K. So that's a formula if you want. It's an identity when you're working in this index notation. Is this familiar? Levi-Civita symbol, that should be familiar. And then if you expand this out, you will get the formula for cross product. But then this allows us to move things around easily. Once you are in index notation, you don't have to worry about position. A and B can go up and down. So that's the advantage, and that's your cross product, because L is a cross product, you write this. And this is a constant, it can come out of derivatives. Is that good?
Yeah, great.
Oh, this one. Okay. And this hits only the R. So what we have here is epsilon I M N M or J and Pn. It should hit all three. It hits this, it hits this, it hits that. But R is the only one it survives. This is independent of R, and that's a constant. So, and this is equal to epsilon I M N. This is delta Mj. Pn. And I'm not caring for whether it's upstairs or downstairs the index, since we are in 3 dimensions, it doesn't really matter. Very soon we will do relativity at that time. Kronecker delta means that I have to replace M and J. So this M with J and get rid of M altogether. So this is N Pn. So that means that the X component of angular momentum, when you take a derivative with the Y component of position, you will get I is X, J is Y, then N has to be Z. That's how you conclude also. Okay, so that's what it is. And similarly, let's do this also. E by D R J E by D T J. This time the P will hit only the P ends. I M N M after the P N J by M J of M. Notice that's slightly different in the sense. If I were to move J on this side, then it brings in a minus. Okay, so what is the change in epsilon, or should I do this also? Yeah, this is also there. D by J K delta epsilon K. That gets onto this. That's delta J K delta epsilon K. That's delta epsilon J. Again, I'm being sloppy with whether it is up or down. Keep it wherever you want. So that's a vector delta epsilon. E by d r j of pk delta epsilon k. That's 0 because this does not depend on. Now we can bring all this together. And we can say the change in the angular momentum, ith component of the angular momentum, is going to be epsilon I j n p n, and this one was delta p, that's delta epsilon j. And the next one is, this is 0. Okay, is that clear? And this is again use the idea of vector product. I want to write it as, if I want to read it as vector product, I can bring this in the front. So it's delta J and Pn. So you learn that how does the angular momentum change under translation? It is delta, not rotations, translation, cross with P. That's how it changes. This is what we got out of Poisson bracket. Can we read this in some other format? Probably yes. After all, it is R cross speed. One could have immediately said that change L is R cross P. So the change in L under translation will be change both, right? R plus delta R, which is delta epsilon, cross with P plus 0, because P doesn't change under rotations. Subtract the origin. That's your Taylor expansion definition, right? Or calculus change, make the change and then subtract the origin, right? And that immediately tells you that, oh, close to this. But it's neat that the Poisson bracket should give you the same. Okay. Any questions on this? Is that very clear?
Yeah, I just have a quick question about the Hamiltonian. So, we still have Hamilton's equations of motions in here, right?
Correct.
So you could substitute the gradient
Yes.
of, okay.
So you mean to say this, right? So this is minus dp by dt dotted with delta epsilon.
Yeah.
Right? Yes, you can. And this is where now you say that, oh, this is independent of time. So I can bring this in and say that this is d by dt of p dotted with epsilon. So like there is one small cheat I made, I shouldn't say cheat. Like this came from the sky, right? Who told you that momentum is the generator of delta epsilon? So what one does typically is that you first take a known operator whose transformation I know. I work that out under Poisson bracket and learn what P is. once I learned this, that this is how it is, then it's true for everyone. So once you have to go through as pretend that you don't know this, usually it's a Hamiltonian because you know how Hamiltonian changes. So that's what the homework was about. All everything is happening with the Hamiltonian. So you learn things using the Hamiltonian where the equations of motion work very well. And once you learn this is the generator, then you plug that in, and that's true for any operator. So that's a power of it. So when you use this process, then you learn that. But to answer your question, yes, I have the freedom to use my equations of motion anytime because it's a constraint. Right? That's like saying in electromagnetism, you have B is equal to del cross A. You're welcome to use that anytime. That's a proper constraint every time. If you're not allowed to use some, there is some issue. Like sometimes it just turns out that you have gone in an area where it's not applicable, but then that's your problem, right? That's you shouldn't have gone there to begin with, or you should have gone with caution. Right? But in general, this is dynamics. You can use Hamilton equations of motion anytime. Yeah, so it's good point. Yeah, it's good point. So allow me to convey that point. So since we said this, so now let's try the so let me highlight this for angular momentum. Hopefully this makes things better. Any more questions before I proceed? Okay, so we did this. I think I need to erase this now. So let's ask the question, how does Hamiltonian or how does angular momentum, how does so let's talk about rigid rotations. And by that, what I mean is that delta of R is delta omega crossed with R. Delta P is delta omega crossed with P, and delta T is 0. And sometimes it is important to give more transformations. Sometimes you have to tell how the Hamiltonian itself transforms. But all this have to be consistent. You can check it again by putting it in. And now let's ask, how does an arbitrary function f change under rotations? So this will be f of r plus delta r, p plus delta p, and t plus delta t, but that's 0 minus of f of r t. Use the standard format. So this is the using Taylor expansion, using calculus. I would say this is the f by r dotted with delta r is delta omega crossed with r. And plus delta f delta p divided with delta omega crossed with t. And there is no time because that's 0. Time is 0, right? Permanence is 0. But then you say, okay, that is what it is. And surely that's a true statement. Using elementary calculus, we can conclude that. But now you want to connect this with Poisson bracket, very much like the discussion we had a minute ago. Let's independently ask, what is the L dotted with delta omega, what is that equal to? And let's also ask what is d by dt of L dotted with delta omega, which we just now did, right? So that's basically these two coming into picture. So let me write this as this is I, and this is K, so this is J, and this is I, this is J, I. So the free index is J now, not I. I is summed out. I is dotted. I'm doing that so that I can use that result that we derived there. So this is equal to partial derivative of I with respect to J times delta omega I. But that's the same as epsilon I J N Pn, and we have delta omega I. What is it as a vector? This is equal to n. This is ij. So free is basically free is j. So I want the I here. So it is minus delta omega crossed with p. J is free, I comes later. So it's p cross omega. I write it as delta minus delta omega cross. Check on me. I cannot read those things. You guys can read it. Okay, the thing. So this is now I J omega I. And that's now I use that result again. Epsilon I mj and that's the same as I want to write j is the free, so j that's delta, that's plus delta omega crossed with r. And now that you notice this, oh, this is nothing but this here. That's nothing but this down here. So you rewrite your change in an arbitrary function under rotations now. So let's call this delta omega, change in an arbitrary scalar function. Right? Scalar function under rotations is equal to f by dr, comma, not comma, dotted with d by dt of L. A lot of vectors around, but hopefully it's clear what is dotting with what. Minus, because this minus I'm writing to begin with. L for the F P. And you say that, oh, that's nothing but the Poisson, right? And then I say Poisson, comma, p dotted with p, or Yeah. Once we have it for any operator, I can do this, I can substitute anything I want for F, and I can ask what happens to it under rotations. Immediate thing you can do is the ones that you already know. How does position change under rotation? How does momentum change under rotation? How does Hamiltonian change under rotation? How does angular momentum itself change under rotation? Right, angular momentum itself is an operator, it can change under rotation, so it's L comma L. From quantum mechanics, what is L comma L as a commutator? What is the commutation relation, quantum mechanical commutation relation between L and L?
The third component of the
Third component, so it is Li Lj gives you epsilon ijk, right? So this is Li Lj, this is quantum mechanical commutator, this is epsilon ijk of Lk. And since it's quantum mechanics, the main difference is that there's an IH bar that shows up. All those things work except for the IH bar missing. All these things works again. This next time you see a quantum mechanics commutator, the way you should read it is that the transformation of L under rotations. This is how it should be. Right? Then you start dropping things. That's what happens. So this is delta omega crossed with that. Once you basically you're multiplying delta omega with the J component, and there is an IH. So a commutation relation tells you how does the first operator change under a transformation generated by the second operator. So that's, and this is calculus. This is how, this is the change in the first operator. So that's the content of the whole thing we are dealing. So we can do that L, but let's take a simpler one. Let's say R, the position vector. So let's ask how does R change? How does the position vector R change under rotation? How does it change under rotations? How does the position vector change under rotations? It's the first. We start with that, but this we got by saying that you make rotations, actual finite rotations, and then you make it infinite spell, and you said that it is possible to write it like that. So always any vector in principle will change like this. Even angular momentum will change like this. That's what I wrote down here, right? Angular momentum changes with it. Always angular momentum has that signature property, but we should see that coming out of here. So this is R comma L after that delta omega. A long way of going, but and you say change the derivative of R. This time I won't bother about the index too much. E by dt. Minus of dr dt divided by this is 0. This is 1. Derivative of position with respect to position itself. that's equal to 1, and derivative of P with respect to L, that's this quantity here, which gives me epsilon, and so this is I P R J P J and that's delta K. Okay. Delta Ki Pj of Li is epsilon I M J M, and that's delta omega I. J is K, epsilon I M K M I. So this is epsilon K I M. And that's an ask equal to delta omega cross, which is definition rotation. And you get the point. I can ask you, I can give you any operator and ask you to do a change, and you should be able to follow these steps. That's the idea. And I'll stop here actually. Hopefully this collects all the concepts we developed. Took all the time to derive the equations of motions, but then the implications of that was done in a very short period.
The next session we have exam minus one question.
And one question, yeah. So this time, should we still be coming at 8:30? No. One question, it's we can come at normal time, 9:30. So what will happen is that I will give the one question exam, but that will have all the questions, and there is a possibility that if I don't think I will be able to do it before, if I by any chance prepare it before, then I'll post it on the web. But that's unlikely. There are too many things going on. So what will happen is that I'll give you the exam, which will have one question, and other questions is take home. So you submit the first question to me right there. If you finish it in 5 minutes, and then you can take it home, or you can finish it in the class and submit to me. That's your choice. And I'm not going to put a deadline on the exam. Based on your convenience, be responsible and submit it. But let's say have a reasonable deadline for yourself. April 31st is April 30th is too late. Too late. Okay. Not even close. You don't even want to go close to that. Okay. So something like that. Reasonable.
How many parts does this question have? Just one part or?
I honestly don't know what I'm thinking. See, if I have all the time with me, and if everything goes well, I would like you to typically there is this nice Poisson. The Poincare generators are the following: P, L, and there is a boost operator. That's the hard part. You have to develop this boost operator, and there is Hamiltonian. 3 plus 3 plus 3, 9 plus 1 time. This is very fundamental. Almost the whole physics comes out of it. And then you can ask every possible commutator, right? PL, what is it? P comma N, what is it? So this is how many combinations can you have? like you have 4 in the first and 4 into 3, about 12, right? And then you can probably invert it. I don't know. How many combinations are there? 12, 4 and 3, right? I think 12, I suppose. And oh, it can be itself too, right? So 4, 4, so 16 of them. That makes sense, like it's a 4 by 4 matrix, you know, and you should be able to write everything. In quantum mechanics, I actually do this, but then I have never actually developed this thing in classical mechanics. In quantum mechanics, it comes out in more natural ways, so there is spin there. It's a little more natural, or it's easy to motivate that. So here I've never done that, so I would like to do that. So if I have all the time, I make you guys do all the commutators, but it's repetitive, but it's kind of nice exercise. I think it will be very useful for you guys. In that sense. But I might end up doing only half of it. I won't work with this. So I won't, because initially I have to develop that, how, where does the n come from instead of giving it to you. So n comes out to be n. So there are 2 possibilities, right? It's Galilean or Einsteinian, right? In Galilean, n is equal to p times t minus mass times r. In Einstein, case m becomes a Hamiltonian. That's the primary difference. Because h is m plus p, right? Or energy is m squared plus p squared. So that's a big change that happens. And there is a small change, L comes in with it. When you go to relativity, for consistency, you need the spin. So it's kind of nice that everything fits in. It almost seems like there is no other choice. Otherwise, you'll wonder where the spin comes from and all that. So that is nice, but at the same time, especially when you go to relativistic, it's a little effort. I don't think I can develop that in a homework. But some limited form of that is what I would like to do, but I might end up that there is no time, and then I might do something else. Something that is more tractable and easy for me to construct. You know. Certain things I can construct in 10 minutes, certain things I will take 2 hours to construct. So does that answer the question? So yeah, it's unpredictable. Thank you. What's that book? Oh, that's German. That's very colorful. Like I think they put their own, everyone put their own color.
This one was very inexpensive for maybe 20, 30 bucks.
Probably out of copyright. They should not even be selling. They are just. Isn't there a rule that after about 70 years or something, books are out of copyright in the US at least? Every country has its own rules of copyright.
There was until, well, it used to be everything became public domain after a certain amount of time, but then Disney messed with it because they didn't want to lose. So
it is not. It is. I'm saying
if you have a good lawyer, you can keep that from happening.
But I think it's a certain amount of time after the creator's death.
Yeah, exactly.
So so Disney still have a big corporation. I doubt Dirac himself has a big. I don't know. It might not have been that long, I guess.
I know that well, there are several of the characters because talking to people that I know that are into the arts and stuff like that would know all these rules. They said that Disney threw a wrench in the old public domain.
It's possible, and I get different parts of the story from different people. Like when I started here, it was made clear to me that you can only have reasonable number of chapters. You cannot put the whole book. Like for example, if I'm teaching Dirac's book, I can put 1 chapter, let's say 3 chapters here and there, but separately. Scan the first chapter, make it available, that's okay. And if it is under behind password in D12, that's okay. But during the pandemic, that was to 2020, there was an email sent that you can put all the chapters. And I thought, no, this doesn't make sense. So I asked them again, and they said, is this pandemic? Is it because of the pandemic? But they made it very clear that no, you can actually put chapter wise, you can put the whole book. And I immediately, what I did was this Physics 205, which is $250 in some sense. Cheaper ones are 100 or something, but it can change any fare from 100. I put the whole book in under D12. Hopefully it helped someone out there. But it was very, someone from the library very clearly wrote it. I clearly asked it again. I repeated the question 2 times and they said, yes, that's what it is. So as far as I am concerned, that's a legal document for me. But the university might have to fight it if something is wrong in there. So I don't know how it goes. It does sound wrong to me that under the library, I mean, it seems like they will lose, at least many students, they will lose money. I don't know. So what I'm trying to say is that different people tell me different things and I go by as far as I can support a legal case against me. I go with that.
What time will you be in your office?
I should be there from now onwards because the next class is an exam. It's at 12:30, so I'll have to come here. So
Okay.
you can even come here. Or maybe what I'm thinking is that I'll take my students to the conference room so that then I can work in my office. I'll see. So look for me here or there.
Okay.
Does that help?
Okay.
And I would say don't stress too much. This is the last